Oh. I don't know why. All right, I have to try something else. This thing is not working. Oh, yes, you should. Can you hear me now? Thank you. Okay. All right, so what do we have so far? We have this problem here. What I'm going to do is always, first, you just have to read it, and you have to understand what you're reading, okay? So you have water is leaking out of an inverted conical tank, okay, at a rate of this. So when I read this, an inverted conical tank, I think of like, you know, a snow cone, okay? If you've ever had a snow cone, right, that's the tank, and it's like dripping out. So sorry, it's leaking out, right? So it's kind of dripping. And notice these units. These units tell me that this is a volume. This is a volume. Why? Because that's a centimeters cubed. Is a volume per minute, right? Volume per minute. So that should tell me that this is going to be some kind of rate of change. Okay. At the same time that water is being pumped into the tank at a constant rate. So this is like we're filling, right? We're filling the cone at the same time. Okay. So not only is stuff dripping out of the cone, and they're telling us the rate at which the things drip out of the cone, they're also telling us that we're also filling the cone. Okay. And they're telling us that the filling of the cone is at a constant rate. So the tank has height 6 meters, and the diameter at the top is 4 meters. So now I'm actually just going to start filling this into my diagram. Okay. Okay. My diagram looks like, you know, this snow cone kind of thing. Okay, and at the top, so here's the top. At the top, it's 4 meters. Okay, and the height from here to here overall is 6 meters. And we are just getting a feel for things right now. Okay, so if the water level is rising at a rate of 20 centimeters per minute, notice this is water level, that's distance, it's linear centimeters. When the height of the water is 2 centimeters, find the rate at which water is being pumped into the tank. Okay, find the rate at which water is being pumped into the tank. Okay, so we've got stuff going in. Okay, we've got drips coming out. Right, so then things are coming out. Okay? And what we're looking at is the rate at which the volume is being pumped into the tank. So let's just write down our givens. Okay. Okay. We know that the volume grows at, what is it, 9,500 centimeters cubed per minute. Okay. The height of the tank. Okay, so the height of the tank is 6 meters, right? And let's see, the diameter at the top is 4 meters. We also know that when, or if the water level is rising at a rate of 20 centimeters per minute when the height of the water is 2 meters, okay, so we can say when height is 2 meters, when height is 2 meters, the volume, actually, the volume, the volume is changing. So I do all of this because if we can produce, and actually I can tell which way it's changing, right? It says the water level is rising. It's not volume. Okay, this is water level. So I need to make sure my units are consistent with what the words say. So this says really that when height of the water is 2 meters, then the height grows by 20 centimeters per minute. Okay, so if I look at this summary and I look back at the original question, then I noticed that when I said that the volume grows, that means that it should be that we're saying that the volume grows by 900. No, what it should be is that it should be decreasing. So I have to change this, and so this is one of the things is that you have to look back at what you did to make sure we've got the details correct. Okay, increasing. Okay, so I just want to now make sure I know what I'm looking for. This is important. What's the question? Okay, what's the question? The question is, what is, okay, find the rate at which water is being pumped into the tank. So knowing that what they mean by water is volume, again, then I know that what is the rate of change of the volume of the water, okay, when the water, you know, is, this is 2 meters, okay, it's 2 meters high, okay. Now, right here, I want to finish filling in this diagram, okay, and I'm gonna write in the variables now, okay. So let's pretend this is the water, right? Here's the water, and let's make up some variables. What are the variables? The variables are height, okay. Let's call it h, okay. This is going to be, h is going to equal height of the water, and that's going to be in what units? I think it's in centimeters, okay. Height of the water in centimeters. The the other variable we need is the diameter of the top of the water. So let's let that be d, is going to be, or so d is going to be, well, it might be better to just use radius. Let's use radius, okay. We can do d in class. Turns out that using radius is slightly more convenient, but we don't have to. Now, I just want to do it that way. R is equal to what? The radius of the water, okay, and that's also going to be in centimeters, okay. Then we have the volume of the water. Volume of the water in centimeters cubed, okay. Now, if we look at the rates of change, okay, what are the rates of change? dH dt, right, is going to be rate. It's going to be, we can call it the speed which the speed at which height is changing. Okay. Then we have dr dt, which we can say the speed at which the radius is changing. And what are the units? What are the units for these? That's going to be centimeters per minute, right? Then we're going to have, this one is going to have the same units, centimeters per minute, okay? And then we're going to have dv dt, which is the speed at which the volume is changing. Okay, and that's going to be centimeters cubed per minute. All right. Okay, so we've defined all our variables and We've defined all our variables and defined our rates of change. So actually, Alexandra, we're really behind, and it actually went really slow, especially while I was gone. And I really want to just keep, extending every deadline. But as it is now, we're not even going to get to, some really kind of important things. And I really, I really don't want to extend it. So I want you to try and do as much as you can. And, the homework is just one part of it. And I know these are kind of long problems, but I really need to kind of push you. So basically, yeah, we'll see, but let's pretend like that's not going to happen, okay? Anyway, all we did so far, I'm just going to stop here and just recap. You just have to read this thing carefully and then write down in a summary everything you know about it. Okay, then you have to define relevant variables. Okay, so all this stuff is just the setup. And if you can get to the point where you know enough to do these things really quickly, then these problems actually become rather quick. But only if you do a lot of them. Okay, and so I had assigned them a week ago and extended them a week. But I understand that these are demanding, so we're going to be able to review them in class today as well, and Wednesday. Okay, so here's all this is just setup. Here's all this stuff. All this is just the setup. We actually have not done very much hard work. Okay, the main thing is just noticing, writing down the variables that we're going to need. And what I want us to do now is start relating the variables. So we have to relate the variables. Okay. Now, oftentimes in these problems, I'll usually give you the geometry that you'll need. But what we need to know is we need to know the volume of a cone, okay? And in general, volumes of cones or volumes of cones or pyramids, or actually pyramids in general, is always equal to 1/3. Okay, and what's the volume? What's the volume of the base of a cone? What is the base of a cone? Oh, yeah, I think that that what you have there is that would be the volume of a rectangular rectangular thing. So the base of a cone is it's 1/3. The base of a cone is a circle. Right. So what's the area of a circle? Pi r squared. Okay. Okay. So it's 1/3. Actually, it's 1/3 area. Yeah. So it's 1/3 pi r squared, which is the area of a circle, times the height, which is just height. Okay. So now notice we have a relationship between r, h, and the volume. Now, if you look at if you translate, if you do a little bit more translating of what we know, if you look at this again, this right here, this translation of all these pieces of information right here is that the volume, oh God, the volume here should say decreasing, God, okay, because it says leaking out, okay, that means the volume per minute, it's dripping, right? So this should tell us that it's decreasing. And if a quantity is decreasing, then its derivative is negative. So we know that we know that this is equal to dv dt. Um, this volume flow rate is negative, so that's going to be negative. So we know that. We know the height of the tank. We know these two things. Okay. So what we have to do is get basically, okay, if we look at what we're looking for, we want to know what dV dt is. Okay. What is that? We don't know. Okay. Now the thing that this one does is it relates V and H. Okay. It relates V and H. But now notice that this problem is kind of tricky because there's two things we have to do. Notice that in the picture here, there's a nested triangle. There's a triangle out here and there's a triangle up here. So if we draw just like the cross section, okay, where we have, okay, here's R, okay, and then here's, this one is 6 and this one is 4, okay. So that means if we're looking at this one, we're going to look at 2. So this is R, this is H. So we have these similar triangles. Okay, similar triangles. Which means that the ratio of height to radius is going to be the same thing as 6 to 2, right? So this is the max diameter, and this is therefore half of it, so it's going to be 6 to 2. So we get the H over R is the same as 3 over 1, okay? And H is equal to 3R. Okay, so I'm going to circle the important formulas. Okay, there's that and there's that. We had to relate the variables. Now, notice that this is the volume. This is the volume of the water. Okay, this is the volume of the water, and that we actually have two things where we have two rates of change. Okay, so this one is tricky in that way because the water is going in and it's coming out. So we have, let's define one more variable where C is equal to the rate water goes in. Okay, so if you come up here, if we were going to label our diagram a little more, see, I don't want you to think that all these problems are always just a linear, you go straight through. You have to look at your setup. You have to go back and revise things. So like this one, okay, you have what? This is, let's let C equal, okay, C is equal to negative 9,500. Right, because that's how much is flowing in, right? And what we want to know is we want to know dV dt. That's how much the water is changing. Okay, so the total rate of change includes the water. So this is equal to the thing we're trying to find. Okay, so the fact that there's this other thing happening, that the water is flowing out, means that we have to write one more little equation here that's going to link everything together and allow us to solve the problem. We know that the total volume, okay, that the total volume is going to be it's going to involve the dV dt, okay, which is equal to, oh crap, Okay, so if you look at this picture, um, I don't know why I keep getting confused with this thing. I'm kind of tired. Okay, so this dVdt, oh crap, it was increasing. I was right the first time. Okay, this one is a negative. So basically, what did I just do? I have to get this straight again. It's eating up time. I'm sorry, but water is leaking out, right? So this isn't actually dVdt. Okay, okay, like this. Okay, so what it's saying, water is leaking out at this rate. Okay, so this is what we're going to call C. Okay, and we're actually I put that in the wrong place, because what I'm looking for is the rate of change of the volume of the water when the water is 2 meters height. The rate of change of the volume of water. Okay, so we know that oh, right. See, I didn't. Oh, I'll try to make another video on this one, but it's like this. Okay. This isn't C. Okay. What is C? The C is, okay. C is, so let's look at it. C is the rate at which the water goes in. Okay. Rate at which water goes in. Okay. So look, how is the volume of this water changing? What's coming out? What's coming out from the problem I read? Whew. And now I have to finish it, even though I think you're all probably thoroughly confused. Look, the volume increases by 9,500 cubic centimeters per minute. That means this, okay, this rate of change is 9,500 centimeters cubed per minute. Okay, this is 9,500 centimeters cubed per minute. What's coming out? We don't know. Okay, we don't know what's coming out, right? And then this is going to be actually different than dVdt. So what's coming out? Let's call it C. Let's name it C. This is going to equal C. Okay, this is going to equal C, and we don't know it. Okay, and therefore, what is happening? What's the rate of change of the volume with respect to time? Okay, how much is going in? 9,500. Okay. Oh shit. Okay. Hey, you guys, I'm really sorry. I just really, this was one of the ones I didn't do beforehand, and I just really kind of fucked it up. So I'm almost corrected it, okay? But now you're probably just, frustrated. I'm feeling a little frustrated myself. Okay. So let me just get this a little better. I promise the next one will be smoother, but let's just get through this, because it's almost done. Like, if I just correct part of how I set this up, it's almost done. Okay, so yeah, I'm really sorry. And then I just tried to be firm with you, and I totally screw up this problem. Oh man. All right, so the freaking thing went away. Ah, okay, good. Let's stop there. I keep going back and forth because I'm getting I keep getting confused with my translation because I was confused the first time, and then I try to fix it, and then well, I'm sure you're feeling somewhat vindicated. Okay, so here it is. I see your comment, Alexandra, and I know, but you know what? I studied and got through it, and I'm not saying everybody who gets through has to go through this shit. All right, so it's cool. I support you. Now, here, let's see. Okay. What do I have to correct? The given thing, I have to identify. It's probably good you see this because actually this is how it gets confusing. Okay, water is leaking out, so it's probably better to just write leaking out. Leaking out at 9,500 centimeters cubed per minute. So this is part of my problem, is that when you summarize, you should just write what's there. Just write what's there, and that's usually what I say. I thought I could be faster for some reason. Okay, I was trying to take shortcuts and got myself confused. Okay, so what does that mean? Where on the diagram is 9,500? Okay, where on the diagram is 9,500? It is right here. It's it's not this. Being a jerk. This is where how the water is coming up, right? So this is 9,500, okay, centimeters cubed per minute, and that is, it's going out, so we should call it negative, right? So it should be negative because it's negative because it's leaving the volume. Okay, so it's a negative rate of change on the volume. What's going in? I don't know. We're going to call that C. Okay, so C is what's going in. C is how much is going in, which we actually don't quite know. But we'll get that as soon as we'll get our final answer of dV/dt. We'll get our final answer of dV/dt when we actually find the relationship between C and -1. So this actually is not that complicated, because what's happening to the volume flow of the water? It's C, but then, so this is how much is going in, right? In, okay, and then we're gonna minus out, right? These are both rates of change, so the rate of change of the volume is C minus 9,500. Okay, so that goes in our thing that relates. Okay, that goes in our thing that's going to relate our variables. So dVt is equal to C, what goes in, minus what comes out. Okay. Okay. Are you going to throw eggs at me for trying to be tough? Thank you, Patrick. Now, that's exactly right. Okay, so does everyone see why this is true? Now, what you may not see is why did I think to combine this? But basically what I'm doing is I'm saying that the volume flow has to incorporate this one here. Okay, and now what you have is you have a formula for a cone in general that has R and H in it. You have a relationship between H and R, and then you have this formula for dV/dt. Okay, so basically all we really know at this point, right, we're going to have dV/dt if we just find what C is, right? So here's our goal, okay, and at this point is to find C, right? But at this point in any related rates problem, we have to now relate the rates, right? So we have to find a relationship between the rates. Okay, so we're going to find C. So our next step is to relate the rates. Okay, and so that's going to be, we have to get one formula that has all the rates. So we have Okay, we have we have V is equal to 1/3 pi r squared times the height. Okay, and we're then gonna, why don't we substitute our relationship up here, right? Which is that h is equal to 3r. So what do we get? Okay, pi r squared times h. Okay, v is equal to 1/3 pi r squared times 3r. Okay, and so if you simplify this, we get this: v is equal to V is equal to, notice, actually we can simplify it even more. It's actually 1/3 times 3 times pi times r cubed, right? You have r times r squared. So then really all you have here are these things canceling out. So now what's our dv dt? Can everyone write down if this is v, then what's the relationship for dv dt? Thank you. That's right. Okay. Thank you. Now, what is the next step? What do we need to do now? We have to substitute. We have to substitute the givens. Okay. Info. Okay. So we did everything. We did everything to relate all these variables together, but we left out some of these important details up here, right? So we want dv dt when certain things were happening, right? We want to know, if you look at the question, when the water is 2 meters in height, okay, and when the height grows by 20 centimeters per minute, okay? So from the thing above, okay, we want to substitute height for 2, and we want to substitute, and we want height for 2 meters, and what is the change in height? It's dh dt. Okay, so dh dt. This is going to be 20. Okay, but there's one more thing, right? We have to use the fact that dv dt. Okay, in this problem, dv dt is c minus 9500, or is it 95? Is it 9500 or 95,000? It's up here. Yeah, 9500. Okay, and then we probably have to convert it to h, right? So here's our rates being related. But oh my, what did we forget? Right? What did we forget? We have to recall that r is equal to a function of t. So we totally forgot the baby. We totally forgot the baby. Why? Because if you differentiate this implicitly, there it is. Inside here you have dr dt. Okay, dr dt. And notice that we don't have things solved for height. So that's a little annoying. Perhaps what we could do is come back up here and say, crap, what we really needed was v is equal to 1/3, and we know that h was equal to 3r, But so what does that mean? It means that r was equal to h over 3. Okay, r was equal to h over 3. So this really is 1/3 pi h over 3 quantity squared times h. Okay, so if you do the same thing, you get 1/3 pi times h squared over 9, which means that the volume, okay, if you simplify this thing, it's going to be, the volume is equal to 1 over 27, or we can say pi over 27 times h cubed. Okay, so that means that our real, the more useful version is dV dt is equal to, it's going to be 3 pi over 27 times h squared times dH dt. Okay, wow. And this means that this will be actually a more useful version because it has only the variables we had givens about. Okay, so we can now do it, and this is pretty annoying. I hope that we can do the next one in a way that's slightly more satisfying. dV dt is equal to, it's going to equal 3 pi over, well, actually we can cancel this thing, and it becomes just 1 pi over 9, and that's going to be times our h squared times dH dt. So Stephanie, the original, so because we squared, notice where that 27 came from? It's because we squared this, okay, and this became a 9, okay, and so these are all in the denominator. Yeah, so h squared over 9, you see I just squared that directly, and so it's 9 times 3 is 27. Pi is in the numerator, okay, so that's why it becomes, oh yeah, there's no 3. That's what you're saying. That's true. Oh no, because we took the derivative. Okay, so once we take the derivative, this 3 comes down. Oh, you're right. Maybe that's what you're saying. A squared. So this should be a 3 right here. And then that 3 will come down, so it becomes over 9. Okay. So the 3. No, because we have to differentiate h cubed, right? So if we do d dt of h, d dt of h to the third, okay, is going to equal 3h squared. Right, so we end up with this thing being h squared. This is just pi over 9 times the baby dH dt. Okay, now we can now substitute things we know. Okay, then we'll be done. And don't we want to be done with this one? Yes, we do. What is dV dt? It's c minus 9500. Okay, it's going to equal pi over 9 when at this specific time this is 2 squared. But then we have to substitute for dH dt, which is going to equal 20. Okay? But there's a little catch here because see this thing right here it's 2 meters. Okay? So how many centimeters is that? It's 200 centimeters. Okay? I know, annoying. But real life problems are ugly. This is somewhat real. So this is actually, okay, this was equal to 2 meters. This one was equal to 2 meters, right? So it's not that one. That one was correct. Okay, it's 2 So then it's 200 in here. Okay, so what does this become? It becomes pi over 9 times 200, which is what? 4, and then 1, 2, 3, 4 times 20. Okay, and so you get, you get C minus 9500 is equal to 8. Is going to equal, this is going to be 800,000 divided by 4, just 800,000 pi divided by 9, okay? I'm not going to try and simplify that, but then so I get C is equal to, this is dV dt, I get C is equal to 800,000 pi, okay, divided by 9 plus 9500, okay? And so this is C, which is equal to the volume flow into the volume rate of change going into the tank. Okay? Whew! It's a bit of a train wreck. I really do apologize. And also for being a jerk. Not really. I'm just feeling the pressure. Just feeling the pressure, too. Don't worry. I put on the pressure on me, too. But it sure does waste time when I screw up, man. Here I will... fine, I had something here. I had my 3.9. So I wanted to show you really quick on this thing. It's fine, I've got it right here. So that was problem 9, and I want to show you what the solutions look like there. Okay, 3.9.8, 3.9. I'll show you what the solutions will look like when you actually go look at the solutions. Okay, they leave out a lot of the setup, and some of it may look just like magic, but some of what I did may look just like magic. Okay, but let me just show you what you see when you actually look at the solutions. Okay, this is how much they write. Okay. Let me try and shrink this thing. Okay. Oh my gosh. Okay. So if you look at the solution they give you, there's no setup, there's no, variable definitions. Okay. They do define the variables, right? But so notice they define the variables and then they just write down directly the translations and all these connections that they made. Okay. So I'll leave that there. You'll be able to look at that. Okay. Now, and I'll just post a bunch of the other solutions you can look at. But let's just, if we recap again, setup is just summarizing everything that's there and trying to make a diagram. Okay. Then what we have to do is we have to relate the relevant variables. Okay. And we have to put them all together to take the derivative to relate the rates. Okay. That's the basic outline, is first summarize and get a diagram, define variables, relate the different variables together, then use substitutions and derivatives to relate the rates together. Okay, so quick, let's do another one less less hastily. Okay, so let's see. I'm going to do number 10. Okay, so number 10 is actually a similar kind of problem because it has a cone in it. Okay, it has a cone in it, and therefore, you know, I believe it uses similar triangles right away. It just does it sometimes in a. I find the order in which they do the things a little peculiar, but so this is 3.9, number 10. 3.9, number 10 just takes a step-by-step approach and doesn't really encourage you to do the same kind of procedure I was doing because it leaves some of that procedure out. So this is 3.9 on line number 10. Okay, and when you were having problems with this, someone said they were having problems. Was it because you weren't quite sure why they were asking each of these questions? This is part 1 of a 5-step question. Okay, but if we read it, we can do our own setup and hopefully understand why they're asking the questions in the way that they do. Okay, so first I want to just I'm going to kind of sketch as I go as we interpret this thing. Okay, a trough is 8 feet long and has ends the shape of an isosceles triangle. Okay, just right here. I realized last semester some people have no idea what a trough is. You know, think like pigs feeding. Okay, right? So it's like, you know, it's going to be something like long, and then there's these, you know, it's like open, but then these things go like this. Okay, there's like a triangular end, you know, and it looks like this, right? And it's kind of open at the top. There it is, the trough. You might think of, you know, pigs coming up to eat in there, right? Okay, so what this is the cross section. It's a cross section of the trough. Okay, so notice that. What are we told? We're told that they are isosceles triangles that are 3 feet across at the top and have a height of 1 foot. That's why here's 1 foot right here, right? And this is 3 feet. But this is like, you know, here's 3, right? And then here's from here to here, that's 1. Tried to fit it on my little drawing. Let me just write it like that. Okay, so 3 is like this, and 1 is the total up and down height. Okay, so here's 3, okay, and here's 1 like that. But so really, the picture we want is right here. It's right there. So this is the edge of the trough. And notice that they don't tell us how long it is, okay? So if I put L there, I don't know how long it is. But it turns out that it doesn't matter, okay? So what we have is we have the cross section. And now what we're going to do is finish reading it and say, okay, 3 feet across the top, 1 feet deep. Then it's being filled with water at a rate of 10 cubic feet per minute. How fast is the water level rising, okay? How fast is the water level rising? Well, what does that mean? What are the variables? Okay, if the trough is being filled with water at a rate of 10 cubic feet per minute, okay, what variable is that describing? What 2 variables are being associated with the trough being filled with water? So water is like pouring in. Yes, it's water. Sorry, it's volume, right? So what are my variables? My variables are going to be V is equals volume of the water, and that's going to be in centimeters cubed, right? So what are we given right here? dV dt is equal to 10 feet cubed per minute. Okay, so that's the rate of change of the volume. Okay, then how fast is the water level rising when the water is 7 inches deep? So we have, here's going to be, here's, I think we should probably call it H. Okay, we should probably just call it H. And say that H is going to equal the height of the water. The height of the water, and so that's going to be in feet. Okay, and notice right here they've already leveled it. So H means that. So what does this mean? This is our question. So here's our rates. What are our rates? The rate is going to be dV dt. Okay, and then H, the rate of change of height, is going to be dH dt. Okay, these are the only two rates we can see right now. Okay, so dH dt is the rate of the height, right? dV dt is a constant, so we can actually just say that it always equals 10, right? It's always being filled the whole time at 10 cubic feet per minute, right? So what's the question here? The question, what is the quest? It is to, we want to know what is dH dt when what? H equals 7. Okay? Okay. So in general, let's relate the variables. Okay, let's relate the variables. We're going to relate the variables by noticing that the volume of a prism in general, this is called a prism, where it's one shape just being stretched out. Okay, it's going to be V is equal to the area of the base, okay, times the area of the height. Okay. Not the area of the height, just the height. Sorry, there we go. Okay, so it's the area of the base times the height. Okay, so what's the area of the base? The area of the base is a triangle, right? So what's the area of the triangle? This is gonna be so volume is gonna be 1/2. What's the base of the triangle? 3. Okay, times the height of the. No, I have to use the variables. Okay, so we have to put all the variables in here. Okay, which I should have put this here, so I forgot to do that. Okay, the B, there's also a B. You can see it right here. Okay, it equals the length of the base of the water, or really the top of the water. Right, it's the base of the triangle. Okay, so from here to here is B. The largest value is 3. Okay, so this is going to be 1/2 B times the height, which is actually the H. Okay, so this thing right here is base times H times, really, I should have called this length. Okay, the length. So here's the area of the triangle. Okay, here's the area of the triangle. Area of triangle. Okay, and then I have to do times the length of the trough. Okay, so here's an important thing to notice, that the length of the trough is actually a constant, which is kind of why we actually don't need to see this. This is a constant, because it does not depend on time. Okay, so it means that when I take the derivative dt of the length, it's going to equal 0. Okay, so the length of the trough for the water never changes. Okay, so what we just found is we found that the volume of the water, is equal to 1/2 B times H times L, where L is something that never changes. Okay, so the last thing is we can relate the base and the height because we have similar triangles. Similar triangles, which that diagram up there shows you. Okay, so we have, notice that that the base is to height as 3 is to 1. Okay, so now what I'm going to do is I'm going to be more careful this time, and I'm going to go up to the question we wrote down and find, we want dH/dt, right? So we're going to now substitute for B to get rid of it, right? So that means B is equal to 3 times H. Okay, so now if we come up with our final function, it's going to look like this. V is equal to 1/2. Okay, I'm going to substitute 3H for B, right? And now I have H, which I know I'm looking for dH/dt, so I should just leave it in there, times H times L. And so the final thing that we need, the relationship between all the variables in the problem, is 3H squared times L. Okay. All right, there's that. Now, what do we have to do next? We have to relate the rates. Okay, so what I'm going to do is I'm going to write this down again. Okay, and then I'm going to take the time derivative of everything. Okay, and I'm going to notice that, oh, we don't actually really need to use implicit differentiation, but I'm going to do it anyway. Okay, so what does this become? This becomes dV/dt, and there's still a product here, so let's use the product rule, which tells us this part is going to be 2 times H if I take the derivative of it, right? But don't forget the baby. The thing we're looking for is dH/dt. Okay, but then we still have this L here. Okay, we still have the L here. And you might be worried, but don't worry, that now I have all this other stuff too, because if I leave this here and I say this is going to be the derivative of L times d dt, like times all this other stuff by the product rule. Okay. Then because this thing is 0, because L doesn't change with time, this thing is 0, so we can just pretty much ignore this whole part over here. And now what we have is this equation is our prized, now we know we're really almost done. Once we have a formula with a relationship between the rates of all the variables. Okay, what can we do? What can we plug in now? What's dV/dt? Does anybody remember what dV/dt is? Yeah, do you remember what they told us the number is for it? So I'm at the point, this is like the final thing, okay? The final thing is we are going to substitute known quantities. Okay, so I'm going to take this, extend it down. From the statement of the problem, we were given dV/dt. Okay, this is up here. dV/dt always equals 10. dH/dt was the thing we're trying to find. Right? And Yeah, it was 10 in this, yeah, sorry, here. So it's 10, okay? And that's going to equal, in this case, this was 2 times the height. What was the height? 2 times, we wanted to know, DHDT. Okay. Uh-oh. Oh, there it is. Okay. When the water is 7 inches deep. So notice that H must be 7, okay, and that L is actually equal to 8, okay. So that's a constant. L is equal to 8, okay, and then here's that thing. So what we're going to do is just plug in those numbers, okay. So we have here's 7, okay, and then times that was this, right, times the HDT, and then I have this one times 8, okay. So simplifying this, we get 7 times 8 is 56 times 2 is 112. So we get 10 is equal to 112 times DHDT. Okay, and that if we divide both sides by 112, okay, if we divide both sides by 112, then we get this, that DHDT is equal to, if you reduce this, it becomes 56 times 556 feet cubed per minute. Okay, so that should be what the answer looks like. Okay, so Alexandra, if you're still here, I may have offended you, but if you are still here, I want you to just look at these steps as sort of breaking down different parts of this process. Okay, so look, right here, this is the answer, right? You won't see this part right here. They're just asking you, using the diagram below, find the relationship between B and H. You may think, wow, that seems like such an easier first step than what I'm applying, but I'm not sure why you'd think to do that unless you started to see the connection between the variables. So, you know, here's all you would put in is, oh, okay, they're walking me through, this is just the similar triangles part, B over H, right? Base over height. That's what you'd enter. So they're just saying, find the relationship between base and height. Well, that's similar triangles. Okay, and then they basically walk you through different parts of this. That eventually, you know, you kind of, I think they, you know, then they ask you to, you know, write the equation for the volume of the trough, right? And then they ask you to write, you know, this final equation for dVdt, and then they have you plug things in, and then they have you solve for. So it's just in a slightly different order than what we were doing, the solution. Okay, I know you probably want to throw tomatoes through the thing, but would you just, I think we really only have time for one more because I screwed up so bad on that first one. But we had, well, were there any questions on this? I mean, probably were, so actually it might be a really good idea to just take a minute, and if you were partially following, at least, you know, tell me tell me if there was a point in which you didn't quite understand what I was doing. Going back. Okay, are there any specific questions about this process? Again, it was first reading carefully, okay, underlying stuff, relating it to, finding the parts that are really derivatives, okay, and then summarizing these variables, and then and the corresponding rates. Okay, I also identified something as that's right, Stephanie. It really does require a lot of practice. That's why this was the only homework for this last week. It may not have been enough, and I didn't hear a lot of questions. But it's true. You just need to practice. And that's really the most important thing about this, is that it's a really involved problem-solving process. So don't worry if you can't finish all of them tonight, right? But try, okay? And just focus on this. Don't worry about any of the new stuff. Just focus on related rates, because it's connected to all the other things. And if you can do related rates problem, I guarantee you the other stuff becomes easier. Okay, there's just some other problems with more difficult algebra, but pretty much the concepts are all here, because it's the chain rule, which allows us to do implicit differentiation, which allows us to solve all these problems where lots of things are changing at the same time. Okay. Now, Alexandra, Anna, Patrick, Wayne, any questions on how I did this? If anyone's still okay. Okay, great. Let's see, what's next? Let's do, you had asked for 13, I think? Yes. So 3.9.13 is an interesting one, because it's sort of the classic ladder sliding down the wall. But in this problem, you're actually looking for just for the rate of change with the angle. Did I say we had to test this? Are we going through 3.8? No, actually, we're going to completely skip 3.8. We're going to start just looking at curve sketching. Basically, it'll only be like the last, probably the last hour, and it's looking at, what the derivative and the second derivatives tell us. If you're just going to do one thing before class on Wednesday, just watch the last video. It's only 7 minutes long, and if you really study what he says in that video, you'll be fine on. That's true. We don't have a test. It's a good day after all. Okay, good. Okay, yeah, read my email, and if you don't get an email, wait, Wayne, did you get my email today? The last video. Okay, that's fine. Don't worry about it. You'll see. It should have come on email. Just at least, it's the one with a highlighted thing. Like, it has an assignment, and it's basically like if you spend the whole thing should just be like 15 minutes. Okay, if you kind of go along and write down important things as you go. It may make it longer by giving a little like questions through there. There's a total of 3 questions in the video, and the last one is just an assignment to turn in. That should be short. Okay. Anyway, don't spend more than 20 minutes on that assignment. Just do as much as you can. Okay, that being said, let's do problem 13. I'm going to start here. My goals are first going to be setting it up. Okay. So this is going to be 3.9 online, number 13, lucky number 13. That is how we do. Okay, it's cranking things out here. Okay, a ladder 10 feet long rests against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1.5 feet per second, how fast is the angle between the ladder and the ground changing when the bottom of the ladder is 8 feet from the wall? Okay, so look at this. They already defined the variables for us. That's wonderful. So what does x mean? Let's summarize it. What is x? X is distance ladder from wall. Oh crap. Small thumbs. Okay, so it equals distance of base of ladder. I know my handwriting is great. Ladder from the wall. Okay, and that's our x, right? Y is the distance of the top of the ladder from the floor. Okay, so one of the things we should notice here is we're asking how fast is the angle between the ladder and the ground changing when the bottom. Okay, so we need to have this thing here too. Okay, so theta is going to be the angle between ladder and the floor. Okay, the acute angle. So let's call it theta. Okay, so notice, look, a ladder 10 feet long. Is this 10 going to change in the problem? Is 10 ever going to change? Yeah, that's right. So it's a constant. It's a constant. So we can just write it into our equations, and we don't have to worry about the length of the ladder changing. Okay. So notice that as the ladder slides down, okay, we may not need this. I'm just pointing things out. dy dt is gonna be negative. Okay, negative because this distance is going to be decreasing in x. Notice that x is going to be increasing dx dt. I don't know how that happened. Dx dt is going to be positive. Okay, it's going to be increasing. Oh, let me fix that. Okay, so maybe you can observe what we need to do next. What do you think we should do next? Okay, so that's constant. Notice that this distance is going to be shrinking, so the derivative with respect to y is going to be negative. It's going to go down. Define how the variables are related. Great! Okay, now before we do that, let's make sure we got all our knowns. Okay, the bottom of the ladder slides away from the wall at a rate of 1.5 seconds. Wow. So that means that's going to be the question. Here's the question. That's right. So let's just translate the question straight to calculus. If dx dt is equal to a positive 1.5 feet per second. Okay, what is d theta dt when all this means when the bottom of the ladder, what does the bottom of the ladder is 8 feet mean for the variables? Yes. Okay, there's some weird thing happening. I'll be a bit more careful. Okay, when x equals 8, right? Okay, when x equals 8. Beautiful. Now, let's relate the variables. What do we need? We actually don't need all of them. The question gives us a hint. Which two variables do we definitely need to relate here? Which two variables do we care about? And they come from the question. The question, if we get the question down right, we should know exactly which two, yes. We should know exactly which two, and so we have a dx dt and a d theta dt. We don't care about y. So we're relating theta and x. Okay? So that means we're going to have to use a trig function. Okay? Trig functions are the functions that relate angles with sides of triangles. Okay? So let me just write this. Let me just draw this triangle, okay, in a slightly different orientation. Maybe that'll help. I always find it's more familiar when the angle's over here. Maybe not. Okay, an x, right? So what's the trigonometric relationship between? Well, you know what? That's crappy. I'm going to do it on the next page. Okay. So what do we have so far? We have a right triangle. Actually, it doesn't matter, but I'm going to do it this way. We have a right triangle. Okay. We have theta here. Okay, let's put our right. We have x here, and we know that this one is 10. What's the relationship between these two things? Anna! Yeah! See, you did. You learned from your trig class real good. Cosine of theta is equal to, right? What is it equal to? It's equal to the adjacent divided by the hypotenuse, which is going to be x over 10. Oh, wow. Bada boom, bada bing. Okay, so here I got cosine theta is equal to x over 10. Wait. We just related the variables. Okay, we related the variables. So now what do we do after we relate the variables? We have to do what? So first we relate the variables, then what do we do? Yeah, we take the derivative in order to relate the rates. So I'm going to do dt for both sides of this. I feel like my color coding is switching back and forth, but it's cosine theta is equal to x over 10. Okay? And what are we going to get when we do that? Okay. What do we need? Can anyone write the answer? Wow. Okay. Does anyone have Yeah, good. So first we take the derivative of the outside function. What's the derivative of cosine? Isn't it minus sine of theta? Okay. Times, don't forget the baby, d theta dt, right? Okay. Then on the other side, it's just a similar. It's a simple. This is the same as 1/10 times x. Okay. So the derivative of it is just going to be 1/10 times dx dt. Wow, you might have been intimidated, but this problem is pretty easy. Okay, so here is, sorry, if I didn't mean it's easy. I'm just saying it's not as hard as it looks. Okay, so what did we do? We just related the rates, and we should stop and celebrate. Minus sine theta times d theta dt is equal to 1/10 dx dt. Okay, I'll write it right here because this is important. What's the last step? Yes, plug in knowns. Okay, so what do we get? There's one more twist in this problem that's helping to exercise your trig abilities, but so I'm going to write it in, okay? Substitute knowns, okay? I'm going to use a little margin over here this time, okay? So we know, remember, wait, what are we trying to find? What are we trying to find? Are we trying to find dx dt? No, we're trying to find d theta dt, okay? But we have that x is equal to 8, and then there we go, okay? So we're going to need this cosine equation too. Okay, so let's look at this. Now, what do we have? We have minus sine of theta. We don't know theta yet. Crap. Times d theta dt, the thing we're looking for, right? This is what we want to find. D theta dt, okay, equals 1/10, but we do know dx dt, okay? We do know dx dt. Dx dt is dx dt is 1.5, isn't it? Oh, it went too far. Okay, so if you remember, dx dt is 1.5. We're going to plug that in. So that's 1/10 times 1.5. Okay, now this is what we want to find, right? But so we still have one unknown. We need theta. Okay, we need theta. Maybe we could have evaluated that up there. But what do we know about theta? We know that cosine of theta. Right, and notice we haven't used the fact that we know that x equals 8. Okay, we know that we used it already. Dx dt is equal to 1.5, but we haven't used this yet. We haven't used that x is equal to 8. So what we can do is plug it in. What did we have? 8 over 10, like that. Cosine theta is 8 over 10. So what can we do to find theta? Okay, so cosine of what is equal to, let's say, 4/5. Okay. Anybody? So we could do it this way. Okay, we could say theta is equal to cosine inverse of 4/5. Yes. Okay. Okay, but now you may have noticed that it might be easier if we had just, because really what we want is theta, right? Or sine theta. Well, so just to follow along, what you would do then is you have minus sine, and then it would be of cosine inverse of 4/5, right? Times d theta dt is going to equal this. Okay, so if we plug this in, we get da 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 times d theta dt equals 1.5 over 10. Okay, so we could do it this way, but notice what we have: sine theta is equal to it's going to be opposite over hypotenuse, right? And if you look at our triangle, we now know it's 10, 8, and this will be y, right? But so then you could use the Pythagorean theorem to solve it, or notice that it's a 3, 4, 5 right triangle, so y squared is going to equal 10 squared, which is 100, minus 8 squared, right? So you could do, here's y squared equals 100 minus 64, which is 36, and therefore y is equal to 6, plus or minus 6, but we're just, so sine theta is equal to 6/10, which is equal to 3/5. And so we could substitute in, and this just taking this and plugging it in for theta will work, but that's messier. It's more clever to notice you can find sine directly from the right triangle because we have 2 out of 3 sides. So you end up with this. You end up with, okay, plugging everything in. You have minus, and instead of sine theta, you have d theta dt, and that's going to equal 1.5 out of 10. Okay, and we just put 3/5 in there. Wow, it's nice. Okay, so finally, d theta dt is just, if you multiply both sides by the reciprocal here, like to solve this equation, you get, okay, I would do negative 5/3, right? So everything cancels, okay, times negative 5/3, okay, and okay, you can cancel some stuff there. Basically, what happens is you get 0.5 over. Sorry, I'll put 1.5 times 5 over 30. Okay, and then this can cancel, and you get you can cancel out the 5 and get a 6 here and get a 1 there. So it's equal to 1.5 over 6. 1.5, to simplify this further, it's 3 halves times 1 over 6. Okay, and so this is, if you cross cancel here, there's a 2 and a 1, you end up with 1/4. Okay. Okay. So, but also I made this negative sign here, so there should be a negative sign here, here, and here. Okay. Basically, if you break this down after substituting in the right things, you end up with this. Okay. And I should have written units up there, but this is really negative 1/4. So notice that the angle is shrinking, but what are the units? It's always radians. When you take the derivative, radians, and then since our time was in seconds, we get radians per second. My goodness. So, quick recap, okay? So, however you end up solving for the unknowns that you need, really the most important part was getting this relationship between the rates, okay? This is really the most important stuff. If you were able to come up with this in a problem, I'll give you most of the credit. Like if you do a summary and you can get to the point where you've written down the relationship between the rates, I'm so happy. Because that is the hardest part. Sometimes problems have an extra step. Like that first one we did is actually quite complicated. Okay, this one is slightly less complicated, but you still had this thing where you had to solve for one more unknown. Okay, so that's the main thing. Yeah, are there any questions on this part? How we did this? And this angle, whenever we're doing calculus, is always in radians. Okay, whenever we're dealing with angles in calculus, we want to turn them into radians. Any questions? Any further complaints? Okay, I'm gonna paste the solution that Web Access will give you here. Yeah, it's a little, sorry, WebAssign. Yeah, that's what they say. Look how quick it is for them. They just write it down. Honestly, if I was not presenting it, that's how I would do it. But really, I actually would not be very happy if I saw you do this, because I really want you to show me your thinking process as you set it up. So I really do want to see definitions of variables, summarize the question, okay, and all that stuff. Any more questions about that problem? Should we set up one more problem? I can go back and do problem 8. Or we just do the setup real quick. These are all straight from your homework, so hopefully they speed up your completion of it. There's actually not too many variables to define in this problem, number 8. So I'm just going to do this. Actually, let me. Anybody? So I recommend going straight to week 10, just for the homework, and going down to the bottom here. See this thing, and following this link. So I'm going to paste it for you right now. You can just click on it for later. Okay. So if you try and get your homework done, just watch this video, do the corrections, and then try and work on the exam review with Ryan this week. Okay? Yeah. So I think that I'm glad it was still helpful, even though I screwed. So I'm glad you're going to go to Epic tomorrow. Just you know, work on related rates, and then maybe do a few tough derivatives, and that's a good way to prepare for class. And if you do this, if you follow this other link and do that one little thing, you should be fine. Okay, and you know what I'll do right now? I'll just post. I'll put the solution to 3.9.8 up for you. It's a little tricky, and I do like it, but I'll say that it's not one of my favorites. So I tend not to put this on one like this on the test. So number 8, okay. So I'm just going to put the solution up here, and I'll post this thing right away under the archives and notes, and you can look at that. Okay, I'll try and fit some more on there. Here it is. Yeah. I'll leave it here for you to look at. But basically, I'm not gonna. Well, I don't know. I could talk to you about it, I guess. Here's this. Okay. So what happens is that we have we have all these different distances in the problem. Okay, and they should be labeled with variables here. Oh no, they're not. They're not. Okay, so they're not labeled with variables, so you have to come up with your own variables. Okay, so what are they talking about? Notice that when they write up their solution, they haven't defined any of the variables. They just write down this is this, and this is this, and this is this. Okay, so which might make actually looking at the solution less useful. Okay, so the setup here is this is home plate, first base, right? So here's the runner right here. Okay, and so we're saying x is equal to distance to first base. Okay, y is the distance, and this is the distance between the runner and the bases. And so what is z going to be? Z is going to be the distance to third, right? Okay, and so this quantity right here, 90 minus x, is really the remaining distance. So this is x from here to here, right? So the runner just ran this far, and they're saying right in this moment, right? Right in the moment, how is this changing, right? And then you can also say, how is this changing, right? So the first part is to look for dy dt is problem 1, okay? Okay, this is literally the rate at which this hypotenuse shrinks. So this distance turns this into a right triangle, right? Turns this into a right triangle. And then we also have a right triangle right here. Okay, but then the sign, notice dx dt would be getting bigger, whereas this should be getting smaller. Right? So as the runner runs from here to here, dz dt, so this is going to be less than 0 because it's decreasing, but dz dt is going to be getting longer, so it's going to be greater than 0. Right? So notice if you look at the answers, here's the final answer for dz dt is a positive number. Okay, and then dy dt, notice they use the word decreasing, so it's a negative number, right? The distance between the runner and second base is shrinking. Okay, so that's how that one goes. Yeah, Alexandra, I think that's actually a huge deal for everyone, and you can see when I'm not organized, I screw up a lot more. So I tried to give you a sort of sequence of things to do, and I also posted the that graphic organizer for the related rates problems. I wasn't using it here, but I have found it very useful to kind of help me stay organized. Okay. Okay, anything else? It's 7 o'clock. Let's see, what is this here? Whatever. Just going to move that thing on. Fix it. This. So y. It's less than 0. That means dx dt is equal to 26. Okay. That's what that means. Okay. That's really, this thing just goes down here, and you have, here's the distance from dude buddy to y to second base, and then the distance from the runner to home, right? And we call this, okay, the distance he ran is x, right? Okay. Oops. Keep doing that. Okay, I'll post these things in a second, and I'll put solutions to some of the other ones up in this document. Okay? So you can study the solutions, but then also practice the ones I've given you, and you should be able to figure it out. Okay, thank you. Hope I wasn't too mean. Oh, thank you, Anna. Glad you could make it. Great. Patrick, good to see you holding it down. Thank you, Wayne. Yeah. They keep you up. Okay, best of luck with everything. Yep. Thank you for your participation and effort. All right. See you soon.
great deals going on right now for the Prius. There's good rebates on it in Toyota. If you're still in the market for this, please let me know. Give me a call, text me, or email me. My number is 650-600-2433. Again, my name is Carlo. You're a retailer in San Bruno. Thank you. Hope to hear from you soon. Bye-bye.
Oh my God, that's so good. I know. Okay, sweetie. My, oh my. My, oh my. What a troubled little child. Daddy's coming.